Ask anyone what they wanted to become when they were a child, and many will tell you they really wanted to become an astronaut. My name is Koen Kegel from Nexus Aurora, and I am no different than any of those children, and chances are that many of you still have this dream, just like I do. So, let us get down to earth and find a way to realize this dream in practice. I will show you the missing part of the equation which is required in order for all of us to actually reach for the stars or, at the very least, low Earth orbit. Space is currently very expensive, but why is that? You might have heard that the most expensive thing humanity has ever built is the International Space Station, which has cost about $200 billion. That is an insane amount of money for something which is essentially the size of a standard passenger airplane cabin used by fewer than 10 people at a time. So, why did it cost that much? First, about 50 extremely expensive launches were required to get all these modules assembled in orbit. Secondly, these modules were all custom built, one-offs, which had to be optimized in terms of mass at almost any cost due to those expensive launches with limited payload capacity. Some companies are currently paving the way in terms of commercial access to space. But how do we make sure that not only the richest people can become astronauts and turn their dreams into reality? Reusability is the key to lowering launch costs. The Space Shuttle aimed to achieve this but completely failed at rapid reusability, which resulted in launch prices of over $1 billion. SpaceX is leading the way into full and rapid reusable rockets, similar to airplanes, and hopefully many other commercial launch providers will follow in their footsteps. In order to lower launch costs order of magnitude further, two things are happening right now. Scale matters, and we see Starship is the largest rocket ever to fly by a factor of 2 in terms of mass compared even to Saturn V. Rapid and complete reusability is made possible at this scale specifically. According to our calculations, Starship will easily be capable to launch up to 500 people to low Earth orbit in a single launch. We currently launch about 4 people per spacecraft at over $50 million per seat. When we get to 500 people per launch with airplane-like reusable launch vehicles, we will get closer to $50,000 per seat, or even lower. So, what is this missing part of the equation I was referring to at the start, which will make access to space more affordable? It is the destination itself. With current space station module designs, we will never be able to create an affordable space station which can handle those hundreds of people on a single launch and where people will actually want to go. We need to realize that a launch vehicle is simply a mode of transport just like an airplane. When you, for example, travel abroad for holidays, you would not want to spend your time inside the airplane which takes you to your destination, but rather spend the time on a beach or walking around the city. Our Orbital Can Station modules provide this destination, which is required to make the next step in human space settlement a reality. The Orbital Can is a mass manufacturable, interconnectable, single launch, 650 cubic meter space station. It accommodates up to 10 people and fits inside the massive payload volume of Starship. It requires just a single launch before being fully operational and ready for the first crew to arrive. No spacewalks required. There are two main volumes. A small can of 70 cubic meters, which houses all ECLIS, all thermal, power and propulsion elements and has berthing ports on both ends. For reference, this module alone is the size of the average ISS module. The other module is the large can, which is a fitting name since it is 580 cubic meters in volume and has up to 6 berthing ports. With almost 8 meters of free internal diameter and a length of 15 meters, many use cases become possible. The Orbital Can allows for scientific, tourism and manufacturing use cases in low Earth orbit, for which fitting interiors can already be built on Earth before launch. One of the first use cases we see for the Orbital Can Station is a direct and complete replacement of the current International Space Station, which is due to retire this decade. Our huge single interior volume allows for much more efficient use, resulting in the ability to fit over 120 scientific international standard payload racks, more than enough to become an adequate direct replacement for the ISS. We also designed a large artificial rotational gravity environment, which fits perfectly inside our large can, allowing for partial gravity exposure, which will benefit health and strength for astronauts on long-duration missions. The payload volume is not the only reason our Orbital Can Station is usable after a single launch. The payload mass capacity helps here as well. For our chosen launch vehicle, Starship, this is likely to be 150 tons, which is about 10 times more than what current launch providers can handle. The payload mass allows for all systems to be integrated on Earth before launch. This includes all life support systems, the complete interior and all power and thermal management systems. A nice benefit is that this payload mass allows us to use commercial off-the-shelf components. We will use car batteries for energy storage, for instance. By sending up more capacity than required, they can each last longer, while also allowing separate battery modules to easily be replaced when required. The payload mass allows for another unique way to save costs. We can build the first versions of the Orbital Can modules with relatively low tech and proven manufacturing methods. We can even choose to partially use the heavier but easier to work with steel instead of relying solely on aluminum or composites. This all greatly eases the speed of manufacturing and the robustness of the modules themselves, which can be fine-tuned while ramping up production. The end result will be a manufacturing system which can rival large aircraft manufacturing speeds, numbers, and costs. The connection between the modules is made by a next-generation berthing port, which we developed in-house and which we are making available open source. It is called the Universal Berthing Mechanism, or UBM. This berthing port has a 3-meter external diameter and allows for a 2-meter rounded square open connection and the feed-through of all piping and wiring required to share life support, thermal fluids, and power. You could see this as a giant universal androgynous connector which you can't plug in wrong. The UBM hatch provides a large cupola domed window for crew to enjoy their views as well. To accommodate hundreds of people in a single space station, dozens of Orbital Can launches will still be required. The UBM allows not only for the safe and quick movement of people throughout such a multi-can station, it also provides safety by internally connecting and sharing ECLIS, thermals and power between modules, providing ample redundancy. In summary, the Orbital Can has the potential to be a low-cost, mass manufacturable, interconnectable and single launch space station. More technical details can be found in our paper on the IAC website. We encourage you to look at it and to let us know what we can improve and contact us about that. Our Nexus Aurora community has room for all people who wish to contribute to making life multiplanetary. We operate globally and would love to welcome you as part of our team. Thanks for taking an interest in the Orbital Can Station, and thank you for helping us improve this design further so that dreaming of becoming an astronaut can turn into reality for all of us.